Welcome, my dear children. Today we are going to discuss a problem in which we have to include the concept both from current electricity as well as magnetic effect of electric current. Problem read like this, little bit lengthy one. A long straight wire carries a current I is equal to 2 ampere. A semicircular conducting rod is placed beside it on two conducting parallel rail of negligible resistance. Both the rails are parallel to the wire. The wire, the rod and the rail lie in the same horizontal plane as shown in figure. Two ends of the semicircular rod are at a distance 1 centimeter and 4 centimeter from the wire. At a t is equal to 0, the rod starts moving on the rail with a speed v is equal to 3 meter per second. See in the figure. A resistor R is equal to 1.4 ohm and a capacitor 5.0 microfarad are connected in series between the rail. At a time t is equal to 0, C0 is uncharged. Which of the following statements are correct? We are given the state maximum current through R is maximum current. There are two options for current. Maximum charge on capacitor, there are two options for capacitor. Now, out of which one is correct, we have to decide. Before that, when a conductor carry current, the concept applied is that it will produce, long conductor carry current will produce the magnetic field around it. And the induction formula or the magnetic induction produced by that current carrying conductor is given by basic formula mu0 I by 2 pi the distance 2 pi r. That formula is known to us due to a conductor, and as distance from the conductor increases, R value decreases. Next thing, when a conductor move perpendicular to a magnetic field, we have heard about what is called the motional EMF. EMF is introduced in that moving conductor. And the EMF formula is given by BLV, the basic formula, standard formula we are applying, where B is the magnetic field existing and L is the length of the conductor, V is the speed which it is moving perpendicular to the magnetic field. Definitely in figure, the magnetic field, if we come back, suppose this is the conductor which carry current I. Now the two rails, here the two rails, and this is at a distance 1 centimeter. 1 centimeter, and the figure that shows. And this is at a distance 4 centimeter. And the separation between these two, therefore, it is clear that 3 centimeter. Now, when current passes through this conductor, we can see that by right hand collapse rule, the magnetic field produced by this one on right hand side, in the figure it is shown on the right hand side. Therefore, on the right hand side, the magnetic field produced by this one is inward. So, it produces an inward magnetic field, and whose intensity is not the same because it is proportional 1 by R. Therefore, it is maximum here, and as we go away from this conductor, the inward magnetic field intensity decreases. And therefore, at each and every point, the magnetic induction is different. One thing. Second thing, here it is connected by means of a conductor like this. Now, when the conductor, irrespective of the shape of the conductor, what we have to take into account, the effective length perpendicular to the magnetic field. Effective length perpendicular to the magnetic field is this one. What may be the shape, irrespective of that shape, the effective length of the conductor that is sweeping the magnetic flux lines is this linear distance bit as shown in figure. Now consider on that rod of length this much, and what is the length of that conductor? That is very clear from here, 3 centimeter. Irrespective of the actual length of the conductor, whether it is a semicircular or a triangular or whatever shape, The effective length that you have to consider is 3 centimeter length of the rod. Consider a small segment of length dx at a distance x from here. Afterwards, we can calculate the magnetic induction there produced by this current carrying conductor. Magnetic induction produced by this current carrying conductor at that point is given by B is given by mu 0 I by 2 pi x. Now our conductor rod length dx move perpendicular to the magnetic field like this in this figure V. The value of V is given there. Now a conductor of length dx move with the velocity V perpendicular to the magnetic field of B. Then there will be a elemental or a small amount of magnetic EMF generated on that small segment. D is given by our basic formula BLV, we can say. Here B is given by mu 0 I by 2 pi x into length of that small segment into dx. With a steady speed and velocity of all the segments are same. This is D. Now for entire conductor, the total EMF is the additive contributed by each element, and the added up we get the total EMF induced across this ray because of the motion of this shaped conductor. Therefore, E is equal to integral D is equal to integral. Now integration, and here the variable is x, and expanding from 1 to 4. Therefore, integral 1 to 4 is 0 I by 2 pi x dx into V. Here that is equal to, and constants we can take out. Now we can see that is equal to mu 0 I V, because they are all the same, by 2 pi integral 1 to 4 dx by x. Because on each segment the EMF induced is different, and therefore we simply add up, because direction of the EMF is the same, and therefore you can add up, and the total EMF is gone by this integration. This gives you the value is equal to mu 0 I V by 2 pi integral dx by x log x between the limit 1 to 4. Even though it is anyway, there is no need of changing the unit. And this on calculation, we can say that that is equal to log 4, that is equal to 2 log 2, is equal to mu 0 I V by 2 pi 2 log 2. Log 2 value is given there in the figure. That is given that log 2 is equal to 0.4. Now substituting this, we get the expression for the value of EMF induced. That is equal to mu 0 4 pi into 10 raised to minus 7 into I, the current through the conductor. Current through the conductor, it is said in the problem. The current through the conductor in the problem, it is said that 2 ampere. And it moves with a velocity that is equal to 3 meters per second. 3 into 2 into log 2 is given there 0.4 or 0.7 by 2 pi. This will get. Now this on simplification, the value is equal to 2 into 2 into 2 into 2 8 and 24. 24 into 0.7 into 10 raised to minus 7. Again, this on calculation is equal to that is equal to 16.8 into 10 raised to minus 7 volt. This is the EMF induced due to the motion of this shaped conductor. in the problem. And whatever may irrespective of the shape, you know that the in the EMF remain the same as this much. Now once you got the EMF, now what is asked? Question is maximum current through. Maximum current we have to find out, and out of this which one is the correct one we have to decide. Similarly, maximum charge, and at what time? It is given that when t is equal to 0. When t is equal to 0, look into the figure. Here it is said that the conductor here what is arranged. Here there is a resistor and there is a capacitor. When t is equal to 0, that means the conductor start moving and this will go and act as a source of EMF this much. Now the capacitor acts as a conductor. It will block only at the steady state. Now when t is equal to 0, you can simply say that it's a conductor. It is a conductor, and when it is a conductor, you can say that the current in the circuit is maximum. Our current in the circuit is maximum. That is called EMF by the resistor in the circuit. That is the current by Ohm's law. And here the R value is given to you. R value is equal to 1.4 ohm. Therefore, current, maximum current is given by. Maximum current is given by. Maximum current when the capacitor start charging or it acts as a conductor when t is equal to 0. EMF is this much. Current is given by 24 voltage. 1.6. 16.8 into 10 raised to minus 7 by the resistor in the circuit. Resistor in the circuit is given 1.4 ohm. And this value on calculation, definitely this value is nowhere near these two values. 10 raised to minus 6. If you calculate this value is over there, and therefore both these two options are wrong. A is wrong, B is wrong. Next thing we have to calculate maximum charge. Maximum charge when not at is equal to 0. Which is the following statement is 0. Series between the rail at t is equal to 0. Capacitor is not charged. But after some time, definitely, the capacitor charges and fully charges. When it is fully charges, then the charge, maximum charge. Maximum charge is given by Q is equal to C epsilon 0 maximum. After some time, not at the when t is equal to 0. It will take its own time, and when it fully charges, the maximum charge is equal to CB, and here is equal to C is 0. That on calculation, C capacity is given 5 microfarad, 5 into 10 to the raised minus 6 into B is given by 16.8 into 10 raised to minus 7. This value on calculation definitely is around 8.4 into 10 raised to minus 12. And therefore that option is here. And therefore the next one is wrong. Even though it's a multiple option question, here the correct option is equal to C. So that finishes this problem. Thank you. See you next class.